In the previous two videos, we had seen what quantum computing is and various physical phenomena such as superposition, interference and entanglement. And in this episode, we are going to begin with the mathematical foundations that explains quantum computing. So we would begin with single systems. First, we'll compare classical information with quantum information using probability, and then see how we can express states in vector form inside a Hilbert space. And then I'll introduce you to Dirac notation and see how matrices can be used to perform deterministic operations. My name is Lochan, and this is the third episode in the series where I make quantum computing accessible and easy to approach. Welcome to Quantum With Lochan. First, let's start with how classical information is represented. Let's assume that we have a system that is represented by n number of physical states, and that is denoted by the variable x. And these systems can take a finite number of values from a particular set, and this set consists of all the states that the system can be in, and that space or that set is known as state space, and it is denoted by the symbol sigma. For example, if we try to see the outcome of a dice roll, the state space for it would be 1 through 6. Most of the times we know the exact state of the system, but we rather prefer to use probabilities to say what is the state of the system. For example, the probability that the die lands on 1 could be 2 by 6, and the probability of the die landing on 2 could be 4 by 6. Instead of representing all these probabilities as it is in fraction form, we can represent them in a vector form. So this is known as a probability vector. There are two conditions for a probability vector: that all columns must sum up to greater than 0. So that basically means that it always must be a positive number and cannot be a negative number. And the sum of a column must always be equal to 1. Representing states in vector form is actually very useful since we can use linear algebra to analyze the states and perform operations on them. All of these vectors exist in a mathematical structure known as a Hilbert space. A Hilbert space is essentially a vector space equipped with an inner product. I will further in this video explain what is an inner product, so bear with me for now. In practical terms, what this actually means is, it is a space where vectors represent states, and vectors can be added, and vectors can also be scaled by numbers. In classical systems, vectors represent probability distributions, and in quantum systems, vectors represent quantum states. So the state of a system can be viewed as a vector inside a Hilbert space. This is why linear algebra plays a very important role when it comes to quantum computing. To represent these vectors more conveniently, we use something known as Dirac notations in quantum mechanics. For representing a column vector A, we can represent it as something known as ket A, where we write ket A in this way. And to represent a row vector, we use something known as bra, and it can be written as bra A, where as you can see, the symbol is just the opposite. If here it is facing towards the right hand side, and here it is facing on to the left hand side. Here's an example of ket A. We write a column vector of entries 1, 3, 7 in a column, and the same entries, when they are written in a row format, they are written in this way, and this is a row vector, and this row vector is known as bra A. If we multiply a bra and a ket, we get a number. This number is known as an inner product. The inner product tells us how two states are related with each other. If we multiply bra A and ket B and we get the output as 1, then it would mean that A is equal to B. And if the answer is 0, then it means that A is not equal to B. And another thing that we can keep in mind is that the variables that are written inside, that is used to name a vector, can always be any variable. It can be a psi or a theta or maybe a A. It's completely up to you. Another way to represent states is using basis vectors. Let's take for an example a state space X, which consists of states 1, 4, 6, 3 inside it. We can represent each single state as a vector form where there is only one entry that's equivalent to 1 and rest equal to 0. For example, ket 4 is an basis vector where it is having 1 in its second entry and 0 in the rest of the entries. So how do we come to the conclusion of why 1 is the second entry and 0 in the rest? That is because of the state space that we have here, where 4 is in the second position in the state space. So aligning that with the vector form, we can write this second entry as 1 and rest as 0. So similarly, if we take ket 6 as another example, ket 6 is in the third position in the state space. So when we translate that into a basis vector, the third entry of the vector would be 1 and the rest would be 0. We can also do a linear combination to say how exactly this works, and that is, now assuming that these two are the only state vectors that appears in the system, we can assume that both of them take half the probability. So we can say 1 by 2 multiplied by ket 4 plus 1 by 2 multiplied by ket 6 is the linear combination of this particular system. Okay, now let's look at deterministic operations. And first let's define the state space of the system, and we have given the state space to be 1, 2 and 3. A deterministic operation is simply an action where one state is pointed towards another state within the state space. Mathematically, we write this as F maps sigma to sigma. Now let's look at an example function. State 1 represents state 2 and state 2 represents state 3 and state 3 represents state 1. And what I mean by that is f of 1 is equal to 2 and f of 2 is equal to f of 3 and f of 3 is equal to 1. Since we represent states as vector, we can use basis vectors to represent the same thing that we have written here. Mathematically, we write this as m multiplied by ket A is equal to ket f of A. Now let's recall the basis vectors for this state space, and when we apply deterministic operation on these basis vectors, ket 1 becomes ket 2, ket 2 becomes into ket 3 and ket 3 becomes into ket 1. From this mapping we can construct the matrix representation of the operation. Each column of the matrix represents the basis vector of the respective function. So the resulting matrix would be 0, 1, 0, 0, 0, 1, 1, 0, 0 for this particular example here. This shows how deterministic operations on classical systems can be represented by linear algebra on vectors. Each column of the matrix corresponds to the image of its particular basis vector. In this video, we saw how classical states can be represented using vectors and probabilities, and then we saw how Dirac notation can be used to represent and describe column vectors and row vectors, and then we also discussed what exactly an Hilbert space is and what inner product is. Deterministic operations can be written as matrices. In the next episode, we'll continue building on these foundations and see what is probabilistic operations and unitary operations on single systems. Thank you.